Okay, so we're looking at the second year Stats and Mechanics textbook, and we're on chapter 4, which is on moments, and exercise 4E, which is on tilting, and we're looking at part C of question 4. Okay, so this is really quite a tricky one. I won't lie, this is my second attempt at the video solution for this. And we've got to think really carefully about what's going on here, and there's a reason why they're saying this is a problem-solving one. So definitely, I'm going to start with a sketch. And I'm going to get this out of the way as well. Okay, so I've got the set. So you must have done parts A and C, A and B to be doing this. Otherwise, it really won't make much sense at all. I'm going to do a new sketch of the rod. So we've got the rod AB. We had a support at C and a support at D. It was a uniform rod, so the weight of the rod of 20 newtons is halfway along it. And they'd attached a 12 Newton weight at end A, and that hasn't been removed. Okay, so that we're adding a second particle, but it doesn't say that we're removing this one. Okay, so what we established in part B was that with this current situation, the rod would tilt about C. So if it was just those two forces, right? Okay, if it was just those two forces, then A would be moving down, so it would start to tilt that way. So that end would move down, and that end would move up. Okay, so we are going to attach 100 Newton weight to stop that happening, and we're going to look at the two extremes of where we can place it. So I think the first situation I'll look at is the maximum value. So basically, so at the moment, if it's about to rotate about C, definitely if I stick, because remember the moment is the force times the distance. So the further we put this force from A or from C, the more of a moment, the more effect it will have. So I'm going to say, well, what about if I stick it all the way down the end there? Okay, so if I stick it quite close to end B, I'm pretty sure that's going to stop it turning. Okay, so I'm pretty sure that is going to be enough to stop it tilting about C. But I might have introduced a new problem, because now, because obviously the 100 Newton weight is much greater than the 12 and the 20 Newtons, what might now happen is if I put that too close to the end, it might make it start tilting about D. So I might now have a pivot at D, and this end might move down, and this end might move up. Okay, so I'm going to figure out how far along, how close to B can I put this new weight without that happening. So if it is just about to tilt about D, then the reaction at C would be 0. Okay, so I'm going to figure out where I can place that 100 Newton weight for that to happen. So I'm going to take moments about D, because there will be a reaction at D, but if I take moments about D, then I don't have to use that. Although I do know the reaction at D, sorry, I said D and put C, reaction at D. So the reaction at D would be 132 newtons. Yeah, the three weights added together, because it would be the only upward force. Okay, so taking moments about D, so I need some distances. So, well, this distance I don't know. This is what I'm trying to figure out. I know that BD is 1 meter, and I know that the 20 newtons is halfway along the 5 meter rod. So I know I can figure out that's 1.5 meters. Although, like I said, you really should have done parts A and B already. So I'm going to assume that you've already calculated most of these lengths previously in the question. And then I need the distance of the 12 Newton force. I'll just stick that down there from D. Well, if I know that BD is 1 meter, I know that that's 4 meters. Okay, so and they're the only 3 forces I need to worry about, because the reaction at C is 0, and I'm taking moments about D. Okay, so I've got these 2 forces which will both be trying to turn it anti-clockwise. Yeah, if my pivot is at D, those 2 are both going to be pulling down and trying to turn it anti-clockwise. So the 12 Newton force times the 4 meter distance plus the 20 Newton force times the 1.5 meter distance, they are both anti-clockwise moments. And this one, so even though all the three forces are pulling downwards, when we're thinking about the turning, this one is going to be trying to turn it clockwise. Yeah, so literally just imagine, this is like a balance beam or something, or a seesaw, a very, very, very uneven seesaw. But you're imagining that that's almost not there because there's no reaction there. So if we have had a different color. So if that's our pivot point, anything pulling down to the right of that, like this force is, will be trying to turn that clockwise. So that moment is going to be the 100 Newton force times the distance x, which I don't know. So I've got 48 plus 30, and that's Newton meters. I don't need to worry about the units because that's not the final answer. Is 100x, so x is 0.78 meters. Okay, but that's not my final answer because that's the distance. That's that distance there. That's the distance of E from D, and they want the distance of E from A. So that's not a problem at all. I know that that's 4 meters. I now know that x is 0.78 meters. So the maximum distance is going to be 4 plus 7.8. And that does make sense. The whole rod was 5 meters long, so I'd be a bit worried if I'd got an answer less than 5 meters. But yeah, so it can be pretty close to the end before it starts tilting. So basically, if we went any further along than that, so if for example we stuck the 100 newtons force on the very end, then the moment would be too great, and that would be enough to move B down and make it start tilting about D. Right, okay, so that's one, that's sort of half our answer. I'm going to do a new sketch for the other situation, because that one's got a bit messy. Okay, so really quickly, so AB even, we've got the 12 Newton force at A, we've got our support at C, and our support at D, we've got the weight of the rod halfway along it. Okay, so, and as we've already said, and as we worked out in part B, if that was the situation, then the rod would tilt. So if that was the situation, and A would be going down, and then B would be going up. So the other sort of extreme of where we could position E is going to be, where can we put it just so it's just strong enough, so the moment is just strong enough to stop that happening. So I'm going to try it. It doesn't matter if this isn't accurate to scale, but I'm going to say, okay, what about if I stick it there? Okay, so how close does it need to be to stop the tilting? Okay, so just get rid of things I don't need. Right, so if it's just about to tilt, then the reaction at D would be 0. Okay, so if it's just so if that happens, if the reaction at D is exactly 0, it won't be tilting, it'll just be on the cusp. Okay, so that was what you had to do for part B. You basically showed that the reaction at D would effectively have to be negative, so would effectively have to be sort of pulling it down, which obviously can't happen. Okay, so if the reaction does just equal 0, as opposed to being negative or being a more sensible value, that means it's not tilting, but it's just about to. So that's the situation. I think that's the tricky thing about this question is sort of considering what the situation is they're actually describing. So again, there will be a reaction at C in this scenario, and it would be 132 newtons, but I don't care because I'm going to take moments about C, which means I don't need to use force at C. Okay, so if you've kind of got to this stage, then now we're almost onto the easy bit, because now we're just onto the calculating the moments. The hard bit, I think, is the problem-solving part. Okay, because I need all my distances from C. So I was told in the original question that AC was 2 meters. I know that the 20 Newton meters is halfway along, so 2.5 meters altogether. So from C, that's going to be 0.5 meters. And this is what I don't know. And so it might well turn out that the 100 newtons needs to be to the right of the 20 newtons, but that really won't matter. Yeah. So basically, if X works out to be more than 2.5, then the 100 newtons is actually to the right of the 20 newtons, but doesn't make any difference to my calculations. Right, okay, so I'm on the home straight. Hopefully I won't mess it up again because I don't think I can do this for a third time. Okay, so what have I got? I have got, so remember C is where I'm pivoting. So I have got that 12 Newton force is going to be pulling the left-hand side down. So that's going to be turning it anti-clockwise. So that's going to be a 12 Newton force times a distance of 2 meters. Okay, then, and that's the only anti-clockwise force because both of these are to the right of C. So they're both going to be pulling the right-hand side down, which is therefore going to turn it clockwise. So, oh, I have made a mistake, but I'm not doing the whole thing again. Right, sorry, I didn't want that distance, did I? I wanted that distance. So that's actually X. Okay, but hopefully nobody stopped watching the video already and thought that was the right labeling. Okay, so I want the distance from C, so it's 100 newtons times that distance of X plus 20 newtons times that distance of 0.5. So 24 is 100x plus 10. So 14 is 100x. So x is 0.14 meters. And again, that's not the final answer. What colour have we used? Okay, so that's the distance of E from C. So I've also got to add that onto the 2 meters to get the minimum value of the distance AE. So 2.14 meters. Okay, so what do we get? 4.78 and 2.14. So basically, and it can equal those. So AE can be anything from 2.14 and 4.78 meters. So basically, so what we're saying is, if it was any less than 2.14, so if it was any closer, the moment wouldn't be enough to stop it tilting. So this end would still move down and it would still tilt about C. So that's what the 2.4 is. The 4.78, we're saying if it was any further along than here, so if it was any closer to B, the moment would be too great and it would move, it would be enough to pull B down. So it would actually rotate about D and lift the left-hand side up. So very well done if you followed that question through. I'm just going to check the answer. Keep my fingers desperately crossed. Yep, we're good.